Hello, my name is Tyler DiBentima and this is Lab 4 on circuits. In this lab, the problem was focused around modeling many different circuits without the actual tools needed to create these circuits in real life. We would also record data such as voltage, current, and resistance of these circuits while also seeing how they react over time. The approach here was to use a circuit simulator in Java that mimicked what a real-life circuit construction toolkit would be like, coming complete with a voltmeter and ammeter. In the end, this toolkit proved to be very useful as we were able to model circuits very accurately and even come up with values such as the time constant of a system, which for one system was calculated as 6.002 seconds, which is very close to the expected value. We started off with a very simple series circuit, and we were able to predict the current in this circuit by looking at the voltage of the batteries in series as well as the resistance of the system. We then observed what happens when the circuit system is broken and the wires are no longer connected. We saw that the current stops flowing through the system and that the potential difference recorded over this gap is the negative of the voltage value of the two batteries in series. Now this is the negative here because the black wire of the voltmeter is the start and the red is the finish, and it is going in the same direction as the current would be, resulting in a negative delta V. After reconnecting the wire and making this a closed circuit system once again, we were able to observe the loop rule in the system. This was done by taking delta V measurements over the batteries and the two resistors and showing that all these values add up to 0, as is stated in the loop rule. On this slide, you can see a graph that shows delta V over time as you go through the circuit. All the aspects of the circuit are labeled below on the diagram, and on top the graph is labeled by A, B, C, D, and E, which all represent different parts of the circuit. In the graph you can see how over A, the battery, delta V goes up by 3, and then you can see across C and E how this value of 3 is lost over the resistors, resulting in an overall round trip of 0 in terms of the value for delta V. Now, interestingly, when we put an ammeter across from a resistor, we notice that the resistance of that resistor is canceled out. This is because the ammeter creates an ideal wire that the current would rather flow through, so the resistance need not be taken into consideration. This explains why our current is read as 0.06 amps, as we're only taking into consideration the 47 ohm resistor. So 3, the voltage, divided by the overall resistance 47 equals 0.06 amps. The second system we looked at was an RC circuit with a 9-volt battery, 10 ohm bulb, and a 0.2 farad capacitor. We observed how over time the light bulb started out very lit up and then dimmed, while the capacitor was charged fully. And then we also observed how when the battery was removed, the capacitor began to let out its charge to light up the bulb. After making those observations, we were able to actually record the charge time and discharge time for both a 10 ohm light bulb and a 20 ohm light bulb in that system. Those values are shown at the bottom of the screen. Our third and final system was very similar to that of our second system, with a 9-volt battery, a 30 ohm light bulb, and a 0.2 farad capacitor. In this step, we paused the simulation and recorded values for the voltage of the capacitor as it was discharging over time. We got values of voltage and the time associated with it for a total of 20 seconds that we would later use to plot on an Excel graph. On this slide, you can see that very graph. On the right, you can see the time and voltage measurements, and on the left, you can see how we actually use these values to find the time constant of our system. These values created the graph in the middle that had a slope that is the negative reciprocal of our time constant that we were looking for. And after a little math, I was able to find that the time constant for the system was 6.002 seconds, which is almost exactly our expected value of 6 seconds that we would get from multiplying the total resistance by the capacitance of our capacitor. Now, if we were to do this lab in real life using an actual ammeter instead of our ideal simulated ammeter, we would have to notice that a real ammeter has a very small resistance of its own, which would mess up our calculations and end up giving us a reading of a lower current than that of the current of the system without the ammeter involved. This would lead to a slightly greater margin of error for our calculations. In our simulation, it is seen that in a circuit without any resistors, the capacitor is charged immediately by a battery. However, in real life, this would not be the case because batteries themselves have very small resistances, so this process would be slowed down by said resistance. Another issue that arises from using real batteries and real capacitors in a real circuit system is that batteries drain and equipment wears down over time. So if one class was to do this experiment or lab on Monday, then they would have a higher voltage in their batteries than, let's say, a class that does this lab on Friday. So the measurements recorded by those groups may be different slightly. Thank you for watching.